Okay. The last time we looked at countability axioms. So these are topological requirements for our space to be able to prove various things. And when we were talking about countability, we were talking about kind of like the basis of the topology, like open set. So for example, the reals is second countable because we have a countable basis for its topology where we just take the open intervals where the endpoints are rational numbers. That's countable. Okay, and so now I want to have a look at separation axioms. So by separation axioms, I'm kind of meaning the ability for the topology to separate out various things. So I'm not talking about it in the sense of connectivity, right? So remember, we had a separation there into open disjoint sets. So here I'm talking about being able to distinguish elements within our space. And so we already had looked at two previous separation axioms. There was a T1 axiom, which states that finite point sets are closed, or even simpler, single points are closed, right? So single points are closed and finite point sets are closed. And then there was a Hausdorff axiom, which said that distinct points can be separated by disjoint neighborhoods. So the picture is kind of like this. Given distinct points, we can get disjoint neighborhoods of x and y. And that separates x and y. And this is also known as the T2 axiom. So it's considered, stronger than the T1. And remember back when we did section 17, we showed that Hausdorff implies T1. So the T stands for Trennungsaxiom. So this is 19th century things like the Germans into things. And there's actually a T0 axiom, which says that distinct points are topologically distinguishable. So what does that mean? So if I have 2 points and the neighborhoods of x is the same as the neighborhoods of y, then we can't topologically tell the difference between the 2 points. Okay. So for example, the indiscrete topology is not T0 because there's only one non-trivial, and there's only the empty set and the whole set, and so we can't really tell the points apart. Okay, so after Hausdorff, the next separation axiom is regular. So let's say we have a space satisfying the T1 axiom, then we say it's regular, or it's T3, if for each a pair consisting of a point and a closed set B, then there are disjoint open sets containing X and B respectively. Okay, so it's called T3. It's obviously better than Hausdorff, right? Because, for example, since X satisfies the T1 axiom, single points are closed sets. So in particular, if B was just a single point Y, then we could separate them. You need the T1 condition, right? Because, for example, if you just consider the 2-point indiscrete space, that is kind of trivially regular, right? Because there are no, what are the closed sets? It's just the whole set itself, so it's trivially. So you have to put that in there as a condition. Okay, What comes next? Well, obviously, we can replace X by a closed set. And if we do that, we get a normal space. Again, misuse of the word normal, I guess. So again, let X be a space satisfying the T1 axiom. And we say X is normal, or T4, if for every pair of disjoint closed sets, there exist disjoint open sets containing A and B respectively. And the same notes occurred before. T4 deserves that name because a regular space is normal, right? Because we can replace A by just a single point X. And again, we need the T1 for the exact same reason that we need it for the regular. Okay. So here we're lining up. There turns out to be other separation axioms as well. There's T3.5, which is completely regular. And so that's between regular and normal. There's T5, completely normal, and T6, perfectly normal. So the use of the word completely, we'll see later on what that means. That means we can do the separation by a continuous function. So by that I mean so for example, so there exists a function f from x to the closed interval 0, 1, such that f of A equals 0 if A is in set A, and f of B equals 1 if B is in B. Right? So that's the definition of completely normal. And it obviously implies normal, right? Because we just take an open interval around 0, like 0 to a third, pull it back, and then that gives us our open set. And similarly, if we do an open set 2/3 to 1, pull it back, that gives us our disjoint open sets containing B. So separating it with a function is kind of like a better way. And perfectly normal means it's normal and closed sets are countable intersections of open sets. And you might think, well, isn't that a countability axiom? It turns out to be a separation axiom because if a normal set is perfectly normal, then it behaves a lot nicer. So later on, we'll see, for example, that normal spaces don't behave nicely with respect to subspaces and products. Like the subspace of a normal space doesn't have to be normal, or the product of a normal space doesn't have to be normal. But if you make it perfectly normal, then those kind of problems disappear. Okay. So this turns out to be a really useful bunch of axioms, just being able to kind of separate stuff out, particularly if you want to prove things like the space is metrizable or other kinds of sort of nice things that are going to happen if you're studying that space. So we've shown that right, we've shown that T4 implies T3 implies T2 implies T1 implies T0, but we haven't shown that it doesn't go the other way. And there are spaces which are Tn but not Tn plus 1. So, for example, here's an example of a space which is Hausdorff, but not regular. So this is our friend Rk. We saw this before. it's the real line, and we have as a topology the basis all intervals a, b, like normally we would have, but also set to the form a, b minus the set k, where k is just the harmonic numbers, right? 1 over n in the possible case. Okay, and so remember, this is a finer topology than the normal topology on the field. Then this space is definitely Hausdorff, right? Because if we have two distinct points, then we can find two intervals, x and y. Then we can find two basis elements of this type that surround them and they're at this joint. So that's no problem. So why is it not regular? So remember what regular means. It means given a point and a closed set, we can find open sets. Well, in this case here, the closed set we're going to look at is k, and the point that we're going to look at is 0. And we want to show that there's no disjoint open set containing 0 and k. First, k is closed in this topology, right? Because there's an open set a, b minus k. So for example, r minus, if a, b is minus infinity to infinity, r minus k is open, so therefore k is closed. Okay. Okay, so let's argue by contradiction. So let's say the space is regular, then there exists open sets u and v. So 0 is going to be in u and k is going to be in v. Okay, so let's have a look at u. U is an open set, so it has to contain a basis element. Okay, so let AB minus KB be the basis element containing 0. Right, there's two possibilities for the basis element. It could be of this type or it could be of this type. But it can't be of this type, right? Because an open set AB, like minus epsilon to epsilon, is going to contain things of the form 1 on n. Right. So it has to be of the type AB minus K. Okay, so if that's the case, then let's just choose n large enough such that 1 on n has to be within AB. Right? So n is bigger than 1 on B. Okay, now let CD be the basis element containing 1 on n and lying in V. Again, there's two possibilities for the type of basis element that could be. It could be of this type or it could be of this type. It can't be of this type, right? Because it contains 1 on n. Okay, so here's our situation. We've got 0, we've got AB, we've got CD. Okay, AB contains 0, CD contains 1 on n. And they're supposed to be disjoint. But let's choose a point Z such that Z is less than 1 on n and bigger than C. If that's the case, then Z lies inside V. But if Z is also bigger than 1 on n plus 1, then Z is not of the form 1 over m, where m is some integer. So Z has to also lie in U. And that's our contradiction. We've come up with something which is both U and V. So this is the main function of this space, just to be a counter example. It's not really that useful for anything else. Okay. Let's have a look at some more examples. Let's look at this space RL. So remember, RL is things which have that as its basis elements. Okay. It's normal. Why is it normal? Well, firstly, we have to show it's T1. Well, it's T1, right, because it's a RL is a finer topology than R. So that means that anything that's open in R is open in RL, and anything that's closed in R is also going to be closed in RL. Okay, so what are we going to do? We've got to show that given any two closed sets, we can get some open sets containing them. Well, let's say we have some disjoint closed sets A and B. And then for each element of A, we choose a basis element that starts at A and goes up to some XA, and we just want it not to intersect B. We can do that, right? Because it's an open set and it's disjoint. And we can do the same thing for the elements of B. For each element of B, take the base element starting at B and going up to some XB, not intersecting A. Again, we can do that because, oh no, sorry, B is a, not intersecting A, right? Not intersecting A, that's the set of those is an open set. So that's why we put that open interval. Not because A or B are open, but because the complement is open.
Wait, so why can we do that?
A and B are closed, so the complement is open. So we just don't want it to intersect B.
Okay.
Right. So we can do that because the not intersecting B is open, so it has an open. And then, right, these are all open sets. We're allowed to take arbitrary unions of them. We take this U and V by construction. They cover A and B covers B. They're open because they're the union of open sets. And by construction, they're disjoint because none of these intervals intersects B and none of these intervals intersects A. So the space RL is normal. What about RL squared? The Sorgenfrey plane, right? The Sorgenfrey plane is not normal. So this is what I was telling you about before, about how a normality is not kind of nice with respect to the other concepts. So here we have a product of normal spaces not very normal. Okay. Again, this is why the Sorgenfrey plane lives, because it's a nice counterexample to things. And again, remember that when we saw it before, the thing that was kind of bad about it was this anti-diagonal x cross minus x, where we showed it was closed and has the discrete topology as its subspace topology. Okay. So any subset of A, any subset of the anti-diagonal is going to be a closed set, right? Because all the points all the points are both closed and open, right? So any subset, it and its complement is also going to be closed and empty in the subspace topology, right? So then it and its complement are then going to be disjoint closed sets in the Sorgenfrey plane. And it's these two things which we are, but we're going to be unable to separate by open sets. Okay. So how do we show that that's not going to work? Well, we do contradiction. So let's assume that there are disjoint open sets UA and VA. So UA containing A and VA containing the complement of A in the anti-diagonal. And so we're going to, so basically what we're going to do is use the fact that the anti-diagonal is disjoint and is the anti-diagonal is homeomorphic to the real line with the discrete topology. That's going to screw things up for us. So let's consider the points, set of points having rational coefficients. Okay, so that's going to be dense in the plane and it's going to be countable. So it's a countable dense set in the plane. And we're going to define a map from the power set of the anti-diagonal to the power set of these rational points by the following. Theta of the empty set is going to be the empty set. Theta of the whole I did something wrong here, didn't I? Oh, that should be delta. Right. So theta of delta is going to be D. Okay, so this is a map from the set of subsets of one thing to the set of subsets of another. So the important thing is that this map is injective. Okay, so let's say we have a subset of the anti-diagonal, which is neither empty nor the whole thing. Then it's going to meet D at some point because D is dense. So therefore, if there's something in that set, this thing is not going to be empty. And if it's not the whole thing, if it's not the whole of delta, then its complement is going to meet something in D. And so therefore, it can't be the whole thing. Okay, now, what happens if we have two proper subsets A not equal to B? Okay, so if A doesn't equal to B, that means there has to exist some point X, which is in one of them and not in the other. Okay, so let's assume X. So assume that X is in A and X is not in B. It doesn't matter if we do that or X in B and X, either X is in A and X is not in B, or X is in B and X is not in A. So without lots of generality, we would consider this. Then X is going to be in UA intersected BB, right? Because that's exactly what this means. X is going to be in U of A, means X is in A. X being in B means X is not in B. Okay. So what does this mean? Why does that imply injective? So what I'm trying to show that theta of A doesn't equal theta of B. Okay, so what's going to happen now? So X is in U of A intersected V of D. So
Because like this joint open set,
sorry?
because the open sets like this joint.
No, it's going to be something like this. So we've got to show then that we want to show that D intersected UA doesn't equal D intersected UB. Because well, X, we've got some X's in A and some X which is not in B. How did a moment ago? So X, so since X is in A and X is in B, X is in U of A intersected B of B. And the point that is then, this set here must contain points of D. There must be points of D that lie in this set, because this set is open and non-empty, and D is dense within the plane. So there are points in D that lie in U of A, and they don't lie in U of B. So therefore, since that's the case, that means these sets are going to be different. That means theta of A doesn't equal theta of B. So this is an injective map. Secondly, there's an injective map from the power set of D to the anti-diagonal, because this is homeomorphic to R, so it has the cardinality of R. D is countable, so it has the cardinality of Z plus. So we can, because there is an injection from the power set of Z plus to R, we just, and those two sets are homeomorphic, then we can get an injection from this set to that set. And so remember, there was this injection from the power set of the integers to the real numbers if you just take or the binomial, the binary expansion of a real number, and you look at the points where it's equal to 1 is going to be some subs. So if you look at it, I guess we're looking at the interval 0, 1, which is homeomorphic to R and has the same cardinality as R. You can get an injection by taking the support of that binary number, i.e. the points where the binary number is 1. So that gives you a subset then of the positive integers that goes to 0, 1, and then you can take that to the real. But anyway, basically the power set of a countable set is the same cardinality as the real, or you can get an injection inside one to the other. But then we just compose those two maps together, and that gives us an injection from the power set of the anti-diagonal to the anti-diagonal. And we know that such a thing cannot exist. Okay, so that was a kind of a different kind of proof, just basically based on cardinality, really. Okay. Alternative definitions. So we know that this often turns out to be quite useful if you actually want to prove that something is regular or something is normal. So this is kind of like a more local definition. So a space is regular if and only given a point of the space, and in the neighborhood of that point, there is a neighborhood, another neighborhood of X, such that the closure of that neighborhood is contained within U. And the same thing for normal. A space is normal if and only given a closed set A and an open set U containing A, there's an open set B containing A, such that the closure of B is within that neighborhood U, within that open set U. Okay, both proofs are exactly the same, so we'll only do one of them. So if a space is regular, and say we're given a point and a neighborhood of that point, then consider X minus U, that's a closed set. Now, since it's regular, right, we have disjoint open sets B and W, B containing X and W containing B. Then the closure of B is disjoint from B. So that does it. Conversely, if we're given a point X and a closed set B not containing X, if we just look at U, the X minus B, right, that's going to be an open set in X. And we have a neighborhood V of X such that the closure of V is in U, and well, we've got V and X minus the closure of V. That's then two open sets. That does our job, and so that shows that X is regular. So as I said, this is quite often a nicer way to prove that things are regular or normal. Okay, so I've already told you that normal spaces don't behave nicely, but Hausdorff and regular spaces behave nicely with respect to inheriting that property. So a subspace of a Hausdorff space is Hausdorff, a product of Hausdorff spaces is Hausdorff, subspace of a regular space is regular, and the product of regular spaces is regular. Okay, Hausdorffness is super easy, right? Because if we have X and Y any 2 points of the subspace of our Hausdorff space, and because they're also points of X, that means there has to exist disjoint neighborhoods U and V, which contain X and Y and X. And then if we just intersect U with Y and V with Y, that'll give us disjoint neighborhoods of X and Y in Y. And of course, those sets are open in Y. The Hausdorffness is really quite nice. What about part of Hausdorff spaces? Okay, so now we have 2 points in the product of Hausdorff spaces. If these points are distinct, then there has to be an index such that x beta doesn't equal y beta. So in that Hausdorff space, we can find disjoint neighborhoods of those points just inside that one space. And then we just take the inverse projection of those. And since projection is continuous, the inverse is going to be of an inverse of an image of an open set is going to be open. So these are going to be neighborhoods that are going to work. So again, the fact of the product of Hausdorff spaces is Hausdorff. It's very straightforward. What about regular? Okay. First off, we have to check that it's T1. But if they're regular, everything is Hausdorff, and if they're Hausdorff, things are T1. So things are T1 because of what we did with the first 2 things in our theorem. Okay, so now, say we've got a point and a closed subset disjoint, a closed subset disjoint from X, right? Since, oh, that should have been regular space there. Since the closure of B, so this is the closure of B in X, when we intersect it with Y, we get B, right? Because B is a closed subset. We can find disjoint open sets U and V of X, containing X and the closure of B. Okay, and now we just intersect those guys with Y, and they work as disjoint open sets of Y containing X and B closure, but B closure intersect Y is just B, so that works. Okay. What about the product of regular spaces? Again, the product is T1 by 2, very right, because if the spaces are regular, they're also Hausdorff. So let's say we have a point. So what we're going to do is we're going to use lemma 31.1. We're going to use the fact that if we're given a point in a neighborhood, there's a neighborhood such as closure is contained within the initial neighborhood. So we've got a point and a neighborhood of that point in that product space. Okay. So what we just do, since it's in an open set U, that means we can find a basis element around that point contained within U. Right? So that means a basis element means that this is a product of open sets, only finitely many of them not equal to the whole space, to the in the product quality. Okay, for each index, choose a neighborhood of our point in that one particular regular space, such that the closure of that neighborhood is contained within that open set. We can do that, right, because each of the spaces is regular. then we proved this before, the closure of V is equal to the product of the closure of the individual neighborhoods, and that's contained within the basis element, and that's contained within U. So that works, of course. Okay. So this whole thing works, right, because we're in the product topology, and the closure of V is equal to the product of the closures in the product topology. So this doesn't. The normal is a whole lot more scary. So for example, if you want to know here's an unsolved problem in topology, so you could write a PhD thesis on this if you like, is omega normal in box topology? Unknown question. So normal and much less well behaved than regular or Hausdorff. Just kind of so, as I said before, these things are not true for normal spaces. As we've already shown, RL is normal, and its hence is regular. So that means that Sorgenfrey plane is regular. But we've seen that it's not normal. So this gives us an example of a space which is T3 and not T4. So that shows we've got that stretched thing. This shows that the product of normal spaces need not be normal. What about subspaces? Well, the subspace of a normal space need to be normal. For example, if we think about functions, if we think about the open interval for R as a subspace of the closed interval to R, right? The closed interval is compact in Hausdorff. Right? It's compact because it's the so this is in the product topology. It's by Tikhonov's theorem. It's a compact space. It's Hausdorff, and so it's normal by a theorem from the next class. Compact Hausdorff spaces are normal. Whereas this space, right, is homeomorphic to R to the R, functions from R to R, and that's not normal. And that's a hard exercise in section 32 that I won't give to you, but you can take it as given that it's not normal. So that's a subspace of a normal space which is not normal. Okay.